In the previous video, you were introduced to the idea of what subshells are, which are 3D spaces in which you can most probably find a specific number of electrons. This is a very abstract idea, and for the first time in this video, we're going to learn how we can represent this information, firstly using something that we call electron configurations, which are a set of numbers that includes three pieces of information: the energy level of the electron, also known as the shell, the subshell, which again is the 3D space in which you can probably find an electron, and thirdly, how many electrons are located in that subshell. So, as always, we start with the easiest element to analyze, hydrogen, because it only has one electron. So, if we write the shell, the energy level at which hydrogen's one electron is located, it would be the number 1. We know that hydrogen falls in this area here, which we know is the S block. That would mean that the subshell, the 3D space where hydrogen's electron is located, is the S subshell at energy level 1, and we know that hydrogen only has one electron, so we would put a superscript 1 here. So again, energy level 1 in an S subshell that contains one electron. Now, if we go down, we see that lithium is located at energy level 2, and if we count lithium's total number of electrons, it would be 1, 2, 3. So what that means is that lithium's electron configuration needs to have 3 electrons in total. So its first 2 electrons would be at the same level as hydrogen's. It would be at the 1s level, energy level 1 in the S subshell. Now, if you remember that S subshells can only hold 2 electrons, that means that lithium's 1s subshell will have 1, 2 electrons. So, first energy level, S subshell, it has 2 electrons. But we know that each S subshell can only have 2 electrons, and that's where we would need a second S subshell, hence 2s. And we know that lithium has 3 electrons. We have used 2 of them in the 1s subshell. Now we need the last one, so 2s1. So again, we know that lithium has 3 electrons. 2 of those electrons are at energy level 1, and in the S subshell at energy level 1, but because an S subshell can only hold 2 electrons, we need to add a second S subshell on top of that at energy level 2, which has 2 electrons. If we take a look at oxygen next, if we follow the same pattern here, oxygen's first 2 electrons are going to be in the 1s subshell, 1s2, then we start adding electrons to the S subshell at the second energy level, 1, 2, but we know that oxygen actually has 8 electrons here, and we have filled up both the 1s subshell and the 2s subshell, so what do we do with the remaining 4 electrons? Well, we remember that oxygen falls within this block here, which is what we call the P block, so this is where we encounter our first P subshell, which is, again, P subshell on the second energy level. This would be the 2p subshell, and oxygen has 4 more electrons in here, 1, 2, 3, 4. So oxygen's electron configuration is 1s2, 2s2, 2p4. Again, 2 plus 2 plus 4 is 8 electrons in total, 2 of them in the 1s subshell, 2 of them in the 2p subshell, and 1, 2, 3, 4 of them in the 2p subshell. If we take a look, mind the spelling here, fluoride, this tells us that this is the ion form of fluorine, which means that it has 1 extra electron here. So if we follow the same pattern, we always start adding electrons at the lowest energy level. So we're going to put 2 electrons in the 1s subshell. Then we put 2 more electrons in the 2s subshell, and we remember that fluoride, again the negative ion, has a full valence shell, which means that instead of 1, 2, 3, 4, 5 electrons, it has an extra electron in the 2p subshell, so this would be 2p6 instead of 2p5. So again, breaking down what these electron configurations mean, start at the energy level, 1, 1s. An s subshell holds 1, 2 electrons. Fill the s subshell at energy level 1. Fill the s subshell at energy level 2. And because this is fluoride, because we have 1 extra electron, instead of 1, 2, 3, 4, 5 electrons, fluoride would have 6 for a full 2p subshell. And that's the general idea. So the idea is when writing electron configurations, we always start by adding electrons from the bottom energy level, and we do so following the blocks or following which subshell we add to next. Now, if we take a look at these two examples here, the first one we're going to look at is the element niobium here, and then the second example we're going to look at is barium here. So if we follow this, let's do niobium first, and then we can take a look at the shortcut. Again, start in the s block for 2 electrons, 1s2, move down to the 2s subshell. Again, these are both full. 2s2. Take a look at the p block here. 1, 2, 3, 4, 5, 6. 2p6 is full. Come down to energy level 3, which would both be full, so 3s2. Go over to the p block at energy level 3, so this would be 3p. 1, 2, 3, 4, 5, 6 is full. Keep repeating this. Come down to energy level 4, 1, 2 for the 4s subshell. And now here, this is where we encounter our first little bit of a trick. Here, if we remember what this particular block is called, this is what we call the D block here, but here, even though this D block here occurs at energy level 4, this is strangely what we call the 3D subshell here. So we will explain why this is when we take a look at quantum numbers in more detail, but for now, even though this first D block here is on energy level 4, this is actually the 3D subshell, and we fill it up completely because niobium is all the way down here. We remember that a D subshell can hold 10 electrons, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The entire 3D subshell is full, and if we go over to the 4p subshell, 1, 2, 3, 4, 5, 6, they're all full. Oops. 4p6. Come down to energy level 5. Here we have the 5s subshell, which is going to be full. And finally, when we get here, remember that the first D subshell is 3D, so the next D subshell here will actually be 4D, and the 4D subshell, we need to count 1, 2, 3 elements over before we get to niobium, which means niobium has 3 electrons in its 4D subshell. Now, the easiest and most consistent way to write electron configurations is simply to follow the periodic table. Start at the 1s subshell with hydrogen and fill them up like this. Move down to 2s, fill it up, 2p, fill it up, 3s, 3p, and so on. There is a shortcut to help you remember which subshells you can fill up. If you draw a grid like this, again, we see all of our S subshells here. There is no 1s, there is no 1p subshell up here, so we start writing from 2p downward. Likewise, there's no 1d or 2d, so we start writing 3d and downward, and so on. And if you draw arrows like this, diagonally from top right to bottom left, you can see the order in which the arrows pass through each subshell is the order by which you fill in the subshells with electrons. So, again, we start up here. 1s is the first subshell we fill, followed by 2s, followed by 2p, 3s, 3p, 4s, 3d, 4p, and so on. And you can see the order of this shortcut matches the order that we've written here. For our final example, we can try it using this shortcut here for barium, which we see is the final subshell that we filled up for barium is the 6s subshell. So if we write out all of the subshells that are full with barium, we start at the top, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, and finally we get to where barium is, energy level 6, the 6th energy level, and barium has both electrons in its 6s subshell, so we would write 6s2. And again, if we use this shortcut here, it works in exactly the same order as you will do if you were to just look at the periodic table and fill in the elements or fill in the electrons in the proper subshell following the element order like this. This takes a little bit of practice, but becomes surprisingly intuitive, even if some people, while doing it, don't exactly know what they're doing. In the next video, we are going to look at a different method of representing electron configurations and electron organization that helps us understand exactly what we're doing when we write electron configurations.